Hi, I'm Phil Burr from ARM, and I'm joined by Jeff Miller from Mentor Graphics. Today we're going to talk about how to make analog smart. So does building a custom SoC have to be so hard? So we're seeing a new wave of custom SoC development, and these are coming from a range of different companies. We're seeing sensor and mixed signal companies creating smart analog and smart sensor components. We're seeing startups who are creating innovative solutions, and OEMs who are looking to reduce costs, reduce power, and differentiate, so to make their products much better. And we're seeing this across a whole range of different vertical applications, all the way from retail to building automation, from agriculture to industrial. So why are people creating custom SoCs? The data shown on this slide is from one of ARM's partners, the S3 group. So this is from a real customer project, and that customer, through having a custom SoC, achieved an 85% reduction in PCB area and 90% reduction in bill of materials. They also had a much more differentiated product. They could add additional features and have a product that was much better than their competitors. And they also managed to have a much tighter control of their supply chain, having one custom SoC rather than many multiple components just makes the whole supply chain much easier. And in many cases, companies are developing custom SoCs to protect their IP. There are companies who you can give a PCB to, and they will come back with a schematic and a bill of materials, making it much easier to copy a PCB. It's much harder to copy a custom SoC. So what is ARM doing to help in custom SoC design? Well, one of the things that we do is we have a program called Design Start. So Design Start is an easy access route to ARM IP. And the slide here is showing access to the Cortex-M0. It's now possible to design with a Cortex-M0 for free. So you can design, develop, and simulate with the Cortex-M0 and System Design Kit. You can then prototype on an ARM-supplied FPGA board that costs just under $1,000, and then you can produce. So when you're ready to commercialize your design, you can move to a simplified fast-track license, which includes the Cortex-M0, the System Design Kit, the Kyle MDK software tools, and support and maintenance, and that's only for $40K. So why the Cortex-M0? Well, Cortex-M0 is ARM's smallest processor, and it's perfect for creating smart analog devices. And typically, the type of custom SoCs we're addressing here have a large amount of analog IP, and typically need to add some processing to that analog IP to create a much more integrated solution. And Cortex-M0 is perfect for this. It provides 32-bit processing capability in an 8 or 16-bit cost point, and it's the lowest and smallest footprint ARM processor at only 12K gates. And really important here is that it provides a low-cost entry into the benefits of all of the Cortex-M family. So this is access to the #1 embedded ecosystem for tools, software, and know-how. So the Cortex-M0 processor is a 32-bit processor. Some people may believe that the code size that you need for that 32-bit processor is actually bigger than an 8 or 16-bit device. And the chart here shows that actually that's just not the case. So we're showing a core mark code across a different number of processors, some 8, some 16-bit. And actually, as you can see that from this, because of the thumb instruction that the Cortex-M0 offers, the code size is actually significantly smaller than the other processors shown on this chart. It's perfect for the smallest form factors of devices, so things like sensors, IoT, and medical devices, and has the benefit of a reduced flash size and power consumption. So I mentioned that ARM Design Start provides simplified access to the Cortex-M0, free for design and simulation, and only $40K for a commercial version. But it's much more than the IP. Through partnering with Mentor Graphics, then we provide free evaluation to EDA tooling, and then simplified and quick access to the tooling itself, and an access to a whole range of different ARM approved design partners. I'll cover those in the next slide. So this slide shows some of the ARM approved design partners. These are distributed across the world for local access, and each have their own skills, whether it's in radio, within analog mixed signal, or in digital. These partners are people that you can trust. ARM has audited these companies for financial stability, for quality, for making sure that they are have experience in designing with ARM, and so on. And so this means that even if you don't have experience of developing silicon design, there are companies that can help you. When people talk about doing a custom silicon, they may have in mind that they need to use the very latest in process technology. For most of the projects that we're talking about here, these projects would benefit from actually using much more mature technology. This chart from IMEC, again one of ARM's partners, shows the number of projects that they have worked on over the last couple of years, and the distribution of those projects against technology nodes. And as you can see, a lot of the projects are using 180 nanometers or 9065 nanometers. And this is for a number of reasons. One, it is much cheaper to use those more mature nodes. Secondly, it's not needed. In fact, sometimes it can be detrimental to use the more advanced nodes because of the nature of the products. Often they're very low power, relatively low processing. And then the third reason is that they often contain analog or RF components, which are often better suited to the more mature nodes. And talked about price for these. Then people may have in mind that it costs multiple $millions to get a test chip on silicon. In fact, at 180 nanometers, you can get a test chip and a multi-project wafer for as little as $16,000. So DesignSight is already helping innovation in custom silicon. Examples range all the way from adding smart intelligence into white goods to being designed to aerospace products, or from IoT nodes to cameras. So what I'd like to do now is to hand over to Jeff, who will explain how Tanner EDA tools can help in custom silicon design.
Thanks, Phil. For anyone who's unfamiliar with Tanner EDA, Tanner solutions have been in the market since 1988, so almost 30 years. We're very widely used for analog and mixed signal ICs, as well as MEMS design. And Tanner was acquired by Mentor just about 2 years ago. Tanner has a wide range of customers for our two main flows. We have an complete analog and mixed signal IC design flow, which includes everything you need to do an analog or mixed signal IC from start to finish. We also have a complete MEMS design flow, including both MEMS layout as well as advanced tools like 3D model generators. Some examples of customers who use our tools: Knowles does MEMS microphones that are integrated in all kinds of devices, have shipped over 8 billion units. FLIR creates IR image sensors, again using our tools. And the Jet Propulsion Laboratory used our tools to create all of the imagers on all of the Mars rovers. IoT really brings some new challenges to our industry. The IoT edge devices in particular are extremely high volume, have to be low cost because there are so many of them, often have physical size requirements, and often have power requirements because they have to be run on batteries for long periods of time. So this is all forcing a higher degree of integration than we've had to do in the past. And one example of this is a TPMS sensor. So TPMS sensors are placed inside each tire of a car, and periodically they use a MEMS pressure sensor to measure the pressure inside the tire and report that via radio frequency to the car, because there's no way to put wires out through a pressurized tire and off of a spinning wheel. These things have to be very low power because the batteries have to last the entire lifespan of the tire. You don't want to be taking your tires off to change the battery. and they have to be produced in very high volume. Hundreds of millions of these have been produced in order to satisfy the demand for these in the automotive market. A single die here handles all of the analog to digital conversion, all of the digital control, as well as the radio itself is on this single die. And this is co-designed with the MEMS pressure sensor. It's manufactured on a separate die and combined into a single IC package. So the only external components beyond that are some passives, the battery, and the antenna built into the valve stem. So this is typical of what we're seeing in IoT designs, where companies start off making a sensor, especially, or a sensor or MEMS device, and they're adding more and more functionality to that and ultimately creating what we call a custom SoC. And so what we see is the sensor companies are adding analog signal processing, ultimately creating a digital interface, and in the most advanced cases, adding digital logic in the form of a microcontroller to do things like sensor fusion, or even to provide user programmable capability. And so at Mentor, we've really prioritized addressing this market at each of the levels. And so Tanner EDA is focusing on the IC aspect of IoT edge device design. The PADS group, of course, is focused on supporting this with PCB design, and the Nucleus group provides embedded software that runs on the embedded processor in order to provide enhanced capability. So let's focus on the Tanner design flow for a moment before I jump into the demo. Here we have analog design and schematic capture in Tanner's SEdit, analog simulation in either Tanner's T-Spice or Mentor's Eldo simulator. In the design entry side, we have the ModelSim and Questa family of digital design and digital simulation tools. And then we have mixed signal analysis by building a co-simulation bridge between Tanner's T-Spice and ModelSim and Questa. And then on the physical layout side, in the analog space, we have the LEdit custom layout tool, physical verification in Calibre, and post-layout simulation using Calibre's XRC combined with the T-Spice simulator. On the digital side, we have the T-Spice, the Tanner LEdit AMS flow, which takes us through synthesis, place and route, and finally digital verification. Finally, we can do chip assembly and physical verification in a combination of LEdit's chip assembly mode as well as Calibre physical verification. And finally, can do mixed signal functional verification, again using co-simulation between the SPICE simulator and the ModelSim digital simulator. So I'd like to give a quick overview of the demo before we jump into it. I'm going to give an overview of the ADC design, just show you how it all fits together. I'm going to simulate that ADC in the T-Spice AMS mixed signal simulator, then connect the custom block to the AMBA Peripheral Bus, or APB. This is the way that you actually connect a custom block into the ARM core and be able to interface through it through software. Then I'll go through some test firmware written in C using the Kyle IDE, and then compile that, bring it all together, and simulate the entire system from ADC, the Cortex-M0, and interfacing using software through the APB to my custom ADC. So this gives you an idea of what it's necessary in order to take your analog sensor and actually connect it in and create a custom SoC using the Cortex-M0 and the Tanner software. So here's our example design. We have an analog sensor, or a sensor that produces an analog voltage as its output. We have a traditional successive approximation ADC. This is the custom part that we'll be focusing on today. This is made of three portions: the DAC, a comparator that determines whether the sensor output is above or below this value, and the control block, which tries successively using a binary search to find the correct value for the analog sensor voltage. It outputs this to the processor through the AMBA Peripheral Bus, and then we can run embedded software to actually read the value. So let me go ahead and jump into the demo. First, I'd like to start by showing you how the ADC8 design comes together in SEdit. So let me pull up our schematic editor. Here in SEdit, I have the test bench for my 8-bit successive approximation ADC. This is what's going to read the signal from the sensor, which outputs an analog voltage, and converts that value to an 8-bit digital value, which then can be sent along to the digital logic. So the architecture of the test bench here, we have an analog input over here, we have various powers and input signals to control the simulation, and then we have the actual device under test here. Let's take a quick look inside. So here, as we discussed earlier, we have our DAC, a comparator, and the ADC control block. And while the DAC and the comparator are implemented as primitive SPICE devices at the transistor level, the ADC control block itself is implemented as RTL in Verilog. So we have a mixture of Verilog and SPICE devices in this design. Let's go ahead and pop up to the top level. At this point, we can go ahead and run a simulation in tSpice. So I'm going to go ahead and launch tSpice, and so we can take a look at the netlist. tSpice operates in a co-simulation mode with ModelSim, so I can invoke the design from tSpice, and tSpice will go through the design and separate the various components of the design into analog components, which are simulated in the SPICE simulator, and digital components, which are simulated in ModelSim. And so they're automatically split up. And tSpice will also go through the design, find all places that need interfaces between the analog and digital simulator, and automatically insert Verilog AMS Connect modules, which will handle the conversion between the discrete states of the digital simulator and the smooth voltage waveforms that are required for a SPICE simulator to operate. So these are automatically inserted. I don't have to do anything special in order to place them where they need to be. So you can see here a .hdl statement brings the ADC control block in Verilog, and then once that's been included into the netlist with the HDL statement, you can simply instantiate Verilog blocks just as you would any normal subcircuit. So I'm going to go into the SPICE simulation settings here because tSpice can run ModelSim in the background during the simulation and just hide it from view so that you can focus on the analog behavior. I think it's a little more interesting in a demo situation to run the simulator in GUI mode. So this will bring up the ModelSim GUI in front of tSpice and allow me to interactively debug, step through the simulation, just as I would in any pure digital design. So I'm going to hit OK here and then launch the simulation. tSpice is parsing the netlist, separating the design out. If there's any Verilog AMS modules, they'll actually be split up between the two simulators. Verilog D modules are automatically compiled into ModelSim, and the SPICE simulation is loaded, convergence is performed, and everything is paused at t equals 0. So ModelSim is now popped up, and here I have my hierarchy of the digital design, and I can go ahead and add some of these signals over here to the waveform viewer. So now that I'm ready to simulate, I'm going to go ahead and actually start that simulation. So I'll just say run -all to kick the simulation off. This is going to run, and you can see the Tanner waveform viewer popping up so that I can see my analog waveforms, and at the same time you can see the digital waveforms populating in the background here because tSpice was running in the background and feeding all these analog waveforms in. So you can see we've done quite a number of conversions here as this design converges and then starts over. So we've done quite a few conversions in that brief simulation. Let's go look over here in the ModelSim side, and you can see that we have the expected digital waveform diagrams and boxcar diagrams as opposed to the analog versions of the signal that come up in the analog waveform viewer. So once we're comfortable with the mixed signal behavior of that block, we can go ahead and close this here, because the real focus today is to talk about how to, now that I've characterized this block, how do I interface it into a Cortex-M0 microprocessor. So let's go ahead and take a look at that. So I'm going to pop up ModelSim now with my Cortex-M0 and show you how how I interfaced my ADC control block into the Cortex-M0. So this is the kit that comes with the Design Start package from ARM, and this includes not only the actual microcontroller, but it also includes the system necessary to operate it. So, various bus interfaces and a simulation environment. So in this case, we have the MCU and the MCU system, and within there you have the Cortex-M0 as well as a number of other systems, and I've plugged my ADC8 into that using a small shim module that I'll show you now. So first of all, this is just the same exact Verilog code that we saw earlier in SEdit. This is the control module for the ADC8. But if I scroll down here, you can see the interface for APB. APB is ARM's AMBA Peripheral Bus, and it's intended as a standardized and easy way for peripherals to connect themselves to an ARM microcontroller or microprocessor core. So it has a standardized interface that we can use for this, involving these signals declared here. So the main ones that we're interested here are the address, the enable signal, and the data signal that will be sent back. So we're going to, when my address is active and I'm enabled, I'll go ahead, we'll do a conversion and then write data back and send the ready signal. And so down here you can see all of the code I needed to write in order to make that happen. And you can actually see it's a fairly short block of code. It fits almost entirely on the screen. Some basic reset logic. We have the start condition, and and just a little bit of logic in order to achieve the behavior I talked about a moment ago, and to plug the ADC control block into the ARM core. Of course, what we need to do now is instantiate this into the overall MCU system so that it's connected into the AMBA bus. So let me go ahead and show you how I did that as well. I'm going to open up the system block. So if I scroll down to the bottom of this, you're going to see just some basic wire definitions and instantiations of parts of the system. And at the very end, I just dropped in a reference to my ADC control block here. So this is the interface between my ADC control block and that shim module that I just showed you a moment ago. And so you can see the signals involved here. I created some new signals for ADC data and clock, as well as the signals that are necessary to drive the DAC and the input from the comparator. So I added those to the signature of the module because those will have to go outside the logic block and actually interface with the analog world. So one other thing that's worth pointing out here is I've interfaced this by plugging it into the port 15 on the AMBA peripheral bus. So there are several ports available as extension ports, and I've chosen 15 somewhat arbitrarily, but this will be important to remember later when we're looking at the software. So, and speaking of software, the ARM microprocessor isn't going to do anything interesting in our simulations unless we add in some test software. So I'm going to go ahead and show you what I've done in that. So I'm going to open up Microvision. This is the integrated development environment used for developing code for ARM cores. And here we have basically, this is just an example that I took from the design start kit and modified for my needs. And so the main thing I've done here is I've added a definition for the register for the ADC data register, and essentially what we have here is the offset is 4000 in hex, and then we have F for 15 because I connected my module to port 15. So that's why you needed to know which port you connected it to, because if I put it on a different one, I need to put that here. The code itself is pretty simple. It prints hello world to the serial port. It performs a read by assigning the data from the ADC data register to a variable. So that actually will perform the read, trigger the ADC. It will do its read and then return a value. And then I print that register value to the serial port, and then because I know what value is supposed to be provided, i.e. 215, I print test passed if I got 215, and I print test failed otherwise. And then I trigger the end of the simulation. So the code is fairly simple, but we just need to exercise the new module. So it's just what we need for this simulation. So once that's compiled, we can just load that in as the ROM for the simulation, and we're about ready to simulate. And so if I go into the test bench here, you can see that I have come up with a very simple model of the analog components of the system. And so assuming there's a fixed input voltage, I can say, well, then the comparator is going to be just whether the ADC DAC data is greater than or less than 215. So that allows me to abstract away the behavior of the analog block for quick simulation. So I can always swap in the analog block and do a full SPICE level simulation, but it will slow things down, and so it's often nice to be able to do things at a more abstract level during your simulations. So I think I'm ready to simulate now. I'm going to go ahead and load this design, and I'm going to add a few signals to the waveform viewer here, so we have something to look at after the simulation is complete. So I'm going to just bring some waveforms over. All right, that should be good. Okay, I'm going to hit run all here, and what we're going to see happen is as the design runs, it's going to start filling in these waveforms. You can see that there's a Verilog print statement here that says conversion result 215. That's coming out of the actual ADC module. We can see the UART printing reg value is 215, and then we see the code printing test passed. So this is pretty cool. We've actually taken something that we made, interfaced it to the ARM core, written software that would actually exercise that new module plugged into the APB, and was actually able to interact with it from software. So in essence, this is all you need in order to build a proof of concept that takes your sensor and your analog to digital conversion block and actually turn that into a custom SoC proof of concept design.